right, today I want to talk about something, momentum, that is used so often in the English language and where it comes from in physics and actually working the physics with it. Now, momentum in physics is the product of an object's mass times its velocity. Now, in the English language, momentum is all about how hard it is to stop something. If a sports team just scored a goal going into halftime, we'll say they have all the momentum right now, and it would take a lot of, in other words, it would take a lot of force or a lot of something to try to stop them. You're doing well in school, you built up some good momentum, easier to keep going once you've already done something. That's the idea of momentum. In physics, we've already talked about momentum and its units, momentum, mass times velocity, and its odd parallel with inertia, how this momentum doesn't have a specific definition in words. It only has one mathematically, and inertia has one in words and not mathematically. Just an odd parallel between the two. We've also already gone over its units, but there they are again for you. Now, in collisions, and I should say in an isolated collision, meaning that there aren't other things happening to it, just two things colliding, momentum is conserved. It's neither created nor destroyed, meaning that it's only transferred between the two objects. So in an isolated spot, we're not going to lose any momentum. So there are three, if you will, types of collisions that we're going to deal with. Elastic collisions means that kinetic energy is conserved. Kinetic energy is the energy of motion. Every time you see this, see energy of motion, I hope you remember that from your middle school classes. In other words, you're not going to lose any of the energy just because the objects are moving or that they have velocity. Objects here will bounce off of each other. And I should say kinetic energy is conserved if it's perfectly elastic. And inelastic, the objects are going to stick together, and there is some energy that is going to be lost in that inelastic collision. Most specifically, whenever objects stick together, work is generally done, causing the objects to crumple in. And that work, remember, work and energy, or actually we'll get to that later, work and energy is the same thing. And you'll see as crumpling happens, energy is lost. And energy is lost in a bunch of other places too. Now, third type, explosion. Objects were stuck together in the very beginning and then actually separate out. That could be because of a spring in between two objects, or one object just pushes another object, like two kids on ice skates. So there are lots of options for explosions. Now, don't think that an explosion is just from some sort of chemical reaction in there. In fact, that's only one type of explosion. It still follows the laws of conservation of momentum. We just don't deal with that all that often, specifically because it becomes way too complex. Generally, whenever something explodes due to a chemical reaction, you have hundreds, if not thousands, if not hundreds of thousands of fragments going each different way. Now, all of those fragments, momentum is conserved, and so the law still applies. One fragment would have positive, one fragment would have negative. We'd have to add up all the components and all this other stuff. We're not going there. We're going to stick to two pieces. One goes left, the other goes right. That's simple with the explosions. Now, here are their respective equations for them. This is, if you will, the conservation of momentum. I mean, check it out. Here's the momentum of object 1 before something happens. Here's the momentum of object 2 before specifically a collision happens. And then they collide. And this would be right before the collision on this side and then right after the collision on this side. So they collide and then they bounce off of each other. So then whatever happens, how fast the momentum of the first object afterwards, momentum of the second object afterwards. Now, if they stick together perfectly inelastic, they're separated at first, momentum of object 1 and momentum of object 2 separated out. This entire left-hand side, if you will, is the beginning side, or the initial. But then, check it out, now they're going to stick together. So I'm going to add the two masses and give them the exact same final velocity. Now, in an explosion, there isn't any initial velocity. So imagine up here on your kinetic that you completely X out this entire left-hand side, because V initial would be 0 for 1, V initial would be 0 for 2. That just leaves you with M1 VF plus M2 VF. Subtract your M1 VF to the other side, and you end up here. All right, I'm going to work on an elastic problem for you now. By the way, please do remember under which conditions energy is conserved and which is not conserved. If objects stick together or they deform, maybe it's a partial sticking as they crunch in before they bounce off. Any time that they stick together, energy is not conserved. That would be an inelastic collision. If they bounce off from each other, they don't crumple in, anything like that, they bounce off from each other, then it's elastic and kinetic energy is conserved. This is a case where I'm going to work with pool balls. Now, pool balls, thankfully, they don't really crumple in much. They stay pretty rigid. Now, technically, they bounce in a little bit, but it's so minute that we can ignore that. In reality, there is no perfectly elastic collision, but we'll finagle this one to work like that. So, kinetic energy would be conserved here, meaning we wouldn't lose any energy. That's actually just something definition-wise you need to know. Now, this problem: cue ball going 1.2 meters strikes an 8-ball head-ons, and the 8-ball was stationary in the middle of the pool table. If the cue ball continues to move forward at 0.25 meters per second, how fast would the 8-ball begin to move? So I recognize whenever I read this problem that the two balls don't combine together, and then there's no sticking part to it there. They stay separate from each other in the end, so I use the elastic equation here. Notice the cue ball continues to move forward at 0.25 meters per second. How fast would the 8-ball end up going? It doesn't imply anything about the two being together. That's how you're going to recognize whether you use the elastic equation or the inelastic equation. If it says anything about sticking, inelastic. If it doesn't say anything about them sticking together at all, it looks like maybe they're separate, go with the elastic equation. So go ahead and write that down. And now we're going to plug in all of the numbers that we know. Now I'm going to choose my cue ball as object 1 and my 8-ball as object 2. And it doesn't matter which object you choose as which. By the way, if there were more things involved in the collision, you just have object 3, object 4, and it would just fit right into this exact same equation. You just have M3 plus VI, M4 plus VI, and over here M3 plus VF and M4 plus VF, however many you had. So I just choose which number my objects are. So I substitute in all my numbers, 0.89 for the mass of the cue ball, which I'm calling object 1, so here's the mass there. Its initial velocity before it strikes the 8-ball was 1.2. Now obviously there is no momentum here for the 8-ball before the collision because it's not going anywhere, so I can just go ahead and write a 0 there. And then after the collision, I'm going to have some momentum for the 8-ball that I'm going to solve for the final velocity over here. And quite evidently, the cue ball is going to slow down, right? It has a slower velocity, thus it's going to have less momentum over here. So some of the cue ball's momentum gets transferred to my 8-ball. So now I'm just going to continue to work the algebra, subtract the 0.225 over and then divide by my 0.78. And so my 8-ball ends up going 1.1 meters per second. Notice that this is going to be positive. I did not mention this in the beginning, but be very, very careful with positive and negative. You, like in all of our other problems, have to choose which way is positive and negative. And I chose the direction of the original cue ball to be positive, which means anything that had gone backwards had been negative. This problem would have been completely different if after the collision the cue ball had bounced back. If the cue ball had bounced back, this would be a negative 0.25 there. So just a word of warning, pay attention to your positive and negatives. That determines direction. All right, we're going to end up trying some of these problems in class.